Question 11. Now, just full disclosure, okay? This question is confusing because it's a coordinate geometry question. And so we're used to thinking about like, you know, air going into a balloon or water going into a trough or whatever. Physical things which I think make it quite easy to visualize and think about, okay, I know what formulas I have to do here, I know what to differentiate. This is coordinate geometry, which you would think we're very familiar with. But when you make, that's okay. When you think about related rates, it really is anything that's changing, and you've got different quantities, okay? So, because I think this is quite confusing, the method I'm going to show you, it's actually a little convoluted. So I'm not at all confident that it's the best way to do it. So if you, as I'm going through this, you're like, hey, why are we doing that? That's a long way around. Then please let me know at the end, because as we've seen before, with these questions, there's often many, many different ways to do it, right? Like I think one question, we did like 3 or 4 different ways, right? So if you have some flash of insight in the middle of me explaining this, then please share it. But otherwise, I'm going to try and explain question 11. So, a point moves clockwise around the circle, x squared plus y squared equals 1. So, unit circle, let's pull it up. It started off well, and then it died. Anyway, okay. Unit circle, so we've got, 1, 1, minus 1, minus 1. Take a sip. And there's a point moving anti-clockwise around it at a uniform speed of 2 meters a second, because, as you do. Okay, so let's put a point on here, and it's moving around in an anti-clockwise direction, 2 meters per second. That's the rate. And later on they tell us that the units of the axes are meters. Okay? Alright, so the question is, find an expression for the rate of change of its x-coordinate in terms of x when the point is above the x-axis. Okay. So, there's a lot there. Let's try and piece it together. Okay? Number 1, find an expression for the rate of change of its x-coordinate. So what are we after, in simplest terms? Rate of change of the x-coordinate, dx on dt, right? Okay. As in, this point, it's got a position around there, and we're just thinking about the the horizontal position. And we want to see how it's changing over time. Okay, good. Now we want to find what this is in terms of x when the point is above the x-axis. So I've already drawn it there, so that's fine. Okay, so we're going to get equals some function, right? And we want everything over here to be x's and no other y's or t's or anything like that. Okay, now, where do you start? Where do you go with this? Well, usually we say, you've got some rate, and then there are other rates which which you've got to get it in terms of. Okay? So I've got this point and it's moving. So the question is, what's the rate over here that's changing? So there's the x and there's the y that's changing, but this thing is not moving according to x or y per se, right? What shape is it moving in? It's moving in a circle, right? It's moving in an arc, yeah? So therefore, what kind of metric am I going to put on here which has a rate of change? Okay. Well, what I'm going to do is put onto there, an arc length, right? And that's the thing that's getting longer and shorter. Because this 2 meters a second is going round and round and round and round, right? So I need a starting point, and the question is set above the axis, right? So I'm just going to say, let's just start there. The question doesn't tell us where we start, so I take it that means it's not really that significant, okay? And it's going up and it's increasing, okay? So if I start here, what kind of shape am I getting? Getting an arc, right? So what should we call this? What should we call this distance here? Any suggestions? I can't call it x, because that's already taken. Any takers? L? Yeah, I'm going to go with L. I think L is good because it's an arc length, right? When we were doing radian measure, we said it's L equals r theta. So I've got an arc, L, and it's growing over time. In fact, it's growing at this rate. So dl and dt is 2. Okay, so let's just keep that filed away. Okay, now, therefore, how is this thing changing as it moves across? This is the tricky part, okay? Let's think about what position am I in at any given time. So, for instance, this thing has coordinates, right? Now, I could call it x, y, but that wouldn't be very helpful, would it? Okay, it doesn't give me any extra information about it. We know, though, that this is a very specific kind of circle, right? This is the unit circle. So what are the coordinates, the x and y coordinates, of the unit circle? Does anyone remember? Good. So it's going to be, these are trig functions. So the trig functions are often called circular functions because they're periodic, they go round and round and round, right? So it'll be r cos theta, r sine theta, where r is the radius. The radius here is 1, right? So this is just going to be cos theta, sine theta. Does that make sense? Those are my coordinates. Okay. So for instance, after time, say 1 second, okay? 1 second passes, so I've moved 2 meters around the circle, okay? Now I just said, let's say we start here. How far have I actually gone? What position will I be in? This is the unit circle, and so what's the circumference of the unit circle? Circumference is 2 pi r, and r is 1. So the whole thing is 2 pi, 6.28 thereabouts, okay? So therefore from here to here, half the circumference is pi, right? 3.14. So after 1 second, I'm expecting to be about 2/3 the way around, yes? So say somewhere like there, okay? So I might say when t equals 1, this is where I am, okay? The arc, L, that I've traced out, right? That length will be 2 meters, right? Because that's the rate that I'm traveling at. So therefore, what I'm trying to get after is what are my coordinates at this point, okay? How do I work out the coordinates if I know the length of this arc I've made is 2? How would I get the coordinates? Good, exactly right. I can get my position up here based on this angle here, right? If my coordinates are cos theta sine theta, okay, then up here, L, that's r theta, is equal to 2. And my radius is just 1, right? So in fact, it just means theta is equal to 2 radians. Is that okay so far? Okay, so this particular point that I was interested in, if theta is equal to 2, its coordinates will be cos 2, sine 2. Whatever those atoms are. Okay. Alright, now let's consider another example. I'm trying to get at how is x moving, okay? I don't want to go another second, like 2 seconds, because then I'd come all the way back down here, and I'm just interested in the top half, okay? So let's think about, say, half a second. When t is equal to a half, where am I going to be? I'm going to be somewhere up here, right? Okay. Now follow the same logic. If the length of my arc was equal to 2 in this case, what's the length of the arc here? Just be 1, right? And we saw that that was equal to theta because the radius is equal to 1, right? So at this point, what will my coordinates be? If theta is 1 radian, it's going to be cos 1 sine 1. Okay, so here's what I'm after. I'm trying to get what's x equal to as it changes over time. When t was a half, x was cos 1. So maybe I should draw this up on the table. When t was 1 second, it was cos 2. You can imagine, if I did go 2 seconds, what would the x coordinate be? Cos 4, right? What's the kind of pattern that I'm observing? How would I explain, if I was at time, just generally speaking, time t, what kind of pattern can I see? Well, whatever this thing is always double the time, right? So it's going to be cos times double, sorry, not times, cos of double the time. Can you see that? Can you see how I formed that pattern? Okay, now, why is this useful? Because if x equals cos 2t, now I can start working toward dx on dt, because I can differentiate this. What's the derivative? It's an easy one. You can do it in your head. Minus, because cos goes into minus sign, and then you do chain rule. So there's the inside, and then turns into sine. Okay, so this is good. at least so far, we've made some progress. dx on dt is that. But of course the question is a jerk, and it says, give me the rate of change of the x coordinate, give me dx on dt in terms of x. Ugh, what a pain. Okay, so I'm in terms of t at the moment. What am I going to do? How can I twist and squeeze this thing so it's in terms of x? How would you do it? How would you go about it? I've got sines. Somehow I've got to squeeze them into cosines. Okay? What's the easiest relationship you know that lets me interchange between sines and cosines? Any takers? Comes from the unit circle. Okay? It'd be I think I heard it, it'd be the Pythagorean relationship, right? Which is that cos squared plus sine squared is 1, right? So let me get rid of this. Cos squared plus sine squared is equal to 1. And this is true for any angle, right? It can be alpha, it can be gamma, it can be 2t, if you like. So let's put 2t's in place because that's what I'm actually dealing with. All right? So I've got cos squared 2t, sine squared 2t, that's equal to 1. Okay, so far so good? Now, these guys here I can immediately replace because I know what cos 2t is. It's x, right? So I've got cos squared, so I've got x squared here. And what I've got here, sine squared 2t is equal to 1. I now want to sort of massage this so I can get towards dx on dt. Okay, how do I do it? Well, let's make it the subject. Let's first start. Sine squared 2t is 1 minus x squared. Okay. I've got it squared, but my derivative is not squared, so I'll need to take the square root of both sides. Okay. So I'll have sine 2t is equal to the square root of. Okay. Now, by the way, is it plus or minus? Plus? Plus or minus? I know that you keep thinking for a little bit. It is plus. It's not as obvious as you might think, though. Okay, it's plus. Now, it does have to do with it being the top half of the circle, but anyway, I'm going to keep going. Okay. Sine 2t, I want minus 2 sine 2t, so I'll slap a minus 2 on both sides. And this is dx on dt. Ta-da! Done. Okay. Now, that was a tough question. At least it was for me. Like I said, it was a little convoluted, right? Because there were a numerous number of insights in there, which they didn't expect you, or they didn't give to you. You had to just sort of get them on your own. Like, what are the relationships between x and y in this theta business? And, moving around, it's radian measure, right? That's hard. And then going from here to here, from here to here was also tricky, because the relationship between those is not immediately obvious. Okay? Now, just to round it out, there's a part B, I think, to the question. Use your answer to part A to find the rate of change of the x-coordinate as it crosses the y-axis. As it crosses the y-axis. So in this case, x is equal to 0. So let's just plug it in. When x equals 0, dx on dt is equal to, alright, what have I got here? Minus 2 times the square root of 1, which is minus 2. Now, the question very helpfully, it's like mocking us, says, why should this answer have been obvious without this formula? You tell me. Why does that actually jump out without doing all of this rigmarole?
I need the horizontal planning of the motion.
Ah, okay, good. Right, so what's going on? All the way around the circle, except at 4 specific points. All the way around, we're moving both up and down and across ways, right? Because we're moving around the circle. But there are 4 points where we're not going in both directions. Here, for instance, we're going straight up, because if I drew a tangent there, it'd be vertical. And here, we're going straight to the right, because I'm going anti-clockwise. Therefore, up here, the tangent again would be horizontal, so I'm going straight across. That's what the negative is about, right? Because I'm going from right to left, okay? So actually, at this particular point, we could have read that result straight off the graph.